Hello class, so for this lecture we are talking about peptides. So we're going to go into some definition first. As a reminder, amino acids are joined together by peptides bonds. And so as far as definitions, when you hear the word amino acid residue, that means joined amino acids. And so the bond that is joining these amino acids are peptide units. You can have dipeptides, which are two amino acids that are joined by one peptide bond. So don't have the confusion when we see di thinking that there is two peptides bonds. There are not two peptide bonds, there are two amino acids. And of course, so two amino acids are joined by one peptide bond. So with tripeptides, there are three amino acids which are joined by two peptide bonds, and so on and so forth. And then you can have oligopeptides, which is just a few amino acids that are joined in some fashion. And then you have polypeptides, which are many amino acids that are joined together. So peptides are linear polymers that can range from 8 to 4,000 amino acids that are joined together. And proteins are molecules that consist of one or more polypeptide chains. And so how peptide bond is formed, as you recall from the foundation of biochemistry, where I told you about a common reaction that you will see will be the condensation reaction. And that is what you see right here for the forming of peptide bonds with two different amino acids. And so when you have these peptides that are formed, they can actually, this bond can be broken by hydrolytic cleavage or by hydrolysis, which is water that is added. And the equilibrium of this reaction favors the hydrolysis of the dipeptide into different amino acids. And so this is the actual favorable condition. And so to make the condensation more thermodynamically more favorable, this carboxylic group must be chemically modified or activated so that the hydroxyl group can be more readily eliminated with the condensation, where you leave where water leaves out, and then you have this peptide bond. And so as far as the structure of a peptide bond, when you have all of these amino acids joined together, you have, as far as what is shown and as far as order, you have the N terminus N, and that's the amino terminal end. And then it goes in a direction where it ends up at the C terminus end. So that is the carboxyl terminal residue. And each of these N has a different pKa. And so you see where it says pKj to represent the amino group. This is more basic, and so that's why it has a higher pKa. And so as far as with this one that's more towards the carboxylic acid group, it has a lower value. And so once again, the isoelectric point is when both the charges of the amino group and the charge of the carboxyl group is both present to have a net of 0. And so how do you find that isolated electric point? Is pretty much taking the average of these pKa's of these different groups. And therefore that is represented right here, where you just add them together and divide it by 2. So that's effectively taking the average. And that will define what is the isoelectric point. And so, as far as a review of this net charge, remember net charge of zero, which is the Zitter ion form. You have both a negative plus a positive. So 1 minus 1, which is equal to 0. If you start to protonate things, this becomes the most protonated form, and so there is no charge on the carboxylic acid group, but there is a charge for the amino group, and so the overall net charge is then just plus 1. But if you have the Zitter ionic form and you just add the base, where this protonated amino group is being deprotonated, and then you have now just the remaining charge of that -1, and so you have a net charge of -1. And so you've seen this slide from the last lecture. We're just going to go more deeper in understanding of each of these points when you have this titration curve of amino acids, where you're starting to see these amino acids acting as buffers. As a reminder, these are the buffer regions. But we're just going to go in more details of understanding this specific chart. And so we have a scenario that is written right here. Relationship between the titration curve and the acid-base properties of glycine. A researcher titrated a 100 milliliter solution of 0.1 molar glycine at pH 1.72 with 2 molar sodium hydroxide solution. She then monitored the pH and plotted the results in the graph shown. The key points in the titration are designated between points 1 and 5. And so here you see it: 1, 2, 3, 4, 5. See that this is very similar to this graph, where you have point 1 is here, point 2 is here, point 3, point 4, and point 5. And so we have several different questions to try to understand this titration curve a little bit better. And so the first point is the pH is equal to the pKa of the carboxylic group. And so we know that the carboxylic group, which is right here, this pK1 is the point where that is showing the carboxylic pKa of the amino acid with the C terminus. And so we know now that this is 0.2. And so that is right here for this particular graph. So that's when we know that the pH value is equal to the pKa value of the carboxylic group of the amino acids. Now, the pH is equal to the pKa of the protonated amino group, which is 0.4 right here. You can see once again that 0.4 is right here. That's pKa2. So that is that equilibrium point where you have that amino group that has, once again, the higher pKa value. That is when that pH of the solution is equal to that pKa of the amino group. So the predominant glycine species is when it's at its most protonated form. So that amino group is protonated, and you have the carboxyl group is fully protonated. That is at this point 1. So that is the most acid that's around, and this is the dominant species in that point of the titration curve. And so the predominant species of glycine, when you have, once again, the net 0, so this is the Zitter ionic point. So you know that is right here, right dead in the middle for point 3. And that is where it is 0 as far as the net charge. And the amino group has the charge of +1, and the carboxyl group has a charge of -1. And so the point where the glycine exists in 50-50 mixture of both the protonated form, because you see there is no negative charge. This is fully protonated, and this is fully protonated. And on this point right here, this is fully protonated, but this is the net 0. So you know the net 0 is right here, and now we're trying to go to the most protonated form. So this point 2 is when you have an equal equilibrium of both the most protonated form and the net 0, the zwitterionic form. We talked about this in the amino acid slides. So that is more so trying to cement those ideas into your brain, that this point is a mixture of the most protonated form and the zwitterionic form, 50-50 ratio. Now we can have a average net charge for the glycine to be 1/2. And that is on point 2, where you have the most protonated form. You have that +1, and there is no charge, so you have 1. And then you have these zwitterionic form, which is 0, which is right here, and you take the average. So you add the two values together and divide it by 2. That equals a +1/2. So that means for right here, on this point, you have a +1, you have a +1/2 at point 2. This is the zwitterionic point, so this is 0. And then now we have the deprotonated and the zwitterionic, so this is the average of -1/2. And this point right here is a full deprotonated form, and so that is the -1 average net charge. And so when half of the amino groups are ionized, that is 0.4 right here, because if you look at it as far as ionized, that is when you, and it says half of it is ionized. This is the ionized form. If it was 0.2 right here, both of the amino groups on this point is ionized. So it is not half of it. But when you on this point right here, we have the zwitterionic form and the most deprotonated form. And so this is the ionized and this is not. And so that is why half of it is ionized. And so we're at this pKa2 is that point. So that is how 0.4 is when half of the amino groups are ionized. And then the average net charge of glycine is 0, which is the isoelectric point. Once again, that is 0.3. I'm just saying this over and over to help cement things into your mind. And so as far as the average net charge of glycine being at -1, that is this point right here. As I mentioned previously, this is the most deprotonated form of glycine. And so you have the negative, and the amino group is deprotonated, and so it's not charged anymore. So the net charge is -1. And once again, 0.5 right here is -1. This point right here, you have now the deprotonated and the zwitterionic. So you have 0 and -1, which average to be -1/2. This is 0. This is +1/2, and this is +1 as far as dealing with the average net charge. And so the isoelectric point, once again, is 0.3. It's right here in the middle. Glycine has its maximum buffer capacity at what regions? And that is right here, point 2 and point 4. We look at this graph once more that we've seen before where we talked about this is the buffer region for each of these amino acids, and this central point is its maximum. And then it starts to lose its buffer capabilities. And that ends the information of diving more deep into the titration curve. Now going into naming peptides. Remember, it is sorted by N terminus to C terminus. It's very important to keep that order. And so while going through that order, you have this example right here where you have serine, glycine, tyrosine, alanine, and leucine depicted here. Here, once again, is serine. This one is glycine. This, remember, the amino acid classification is based off of these R groups and the naming convention. And so this one is tyrosine. This one is alanine. And this one is leucine. To simplify matters, chemists name peptides and protein structures by using 3-letter abbreviations for the amino acids, which is listed right here in this form. And the abbreviation for the amino acid residues are with dashes to show the peptide bonds. So these are the dashes to represent the peptide bonds. The peptide bonds are peptide bond area are shaded in light red, which is shown right here, and the R groups are in red right here. And so that is the overall naming of peptides. And so amino acids can not only be joined together by peptide bonds, but also by disulfide bonds. And so remember back in the last lesson where I stated that cysteine can be oxidized. This is what is happening when that cysteine is oxidized and it forms a disulfide bond. So the most common cross links are disulfide bonds formed by oxidation of a pair of cysteine residues. Extracellular proteins often have several disulfide bonds, whereas intracellular proteins usually lack them. And that concludes the lecture on peptides.